Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electricity and magnetism, and so far we have discussed about electric field intensity, basic concepts related to that, electric potential, potential difference, and all the related concepts. So in this video we are going to discuss about another important concept related to electric potential or potential difference, which is equipotential surfaces. So we have already discussed about how the presence of a source charge at any point in space, it produces electric field, and how what is the value of the electric potential at any point due to a single point charge or a group of point charges. Okay, so the concept of equipotential surfaces is, as the name suggests, it is related to electric potential. So any surface which has the same electric potential at every point on it, every point on the surface, it has the same electric potential, that is called as an equipotential surface. Okay, so equipotential surface means surface which has the same potential at every point. Okay, every point on it. So equipotential is equal potential. Okay, that. So these two combined, equipotential surface. So let us say we have a surface here which is an equipotential surface. So here let there are 2 points A and B. So if it is an equipotential surface, then potential at A is equal to potential at B, or it means the potential difference between A and B, okay, VAB is VA minus VB, which is equal to 0 volt. So we can say sorry, that the potential difference between any 2 points on an equipotential surface will be 0. Okay, any 2 points on an equipotential surface will be 0. So there are some properties associated with equipotential surfaces. We'll discuss them one by one. So here this is an equipotential surface. Don't worry about the electric field vector, we will come to that. Okay, here just understand that A and B, there are 2 points which are at the same potential, the potential difference between them is 0, and between any 2 points on the equipotential surface, since they are at the same potential, the potential difference will always be 0. So properties of equipotential surfaces. First one, no work is done in moving a charge on an equipotential surface, or we can put it in another way, that is, work done in moving a charge on an equipotential surface is 0. Why is that? Now we know that we have already discussed while discussing electric potential and potential difference that the electric potential at any point, okay, any point, is the work done in moving a charge, a test charge Q0, from infinity to that point divided by the test charge. Okay, so here at point P the potential will be the work done in moving the charge from infinity to that point divided by the test charge. Similarly, VA will be work done in moving the charge from infinity to A divided by the test charge value. VB will be W phi B divided by Q0. And the potential difference between 2 points, let's say between VA and B, it is the work done in moving the charge from A to B, A to B divided by the test charge value, which is basically VB minus VA, because VB is at a higher potential than A, because more amount of work will be done in moving the charge to take it to B than it to A, because B is farther from infinity than A. Infinity is just for the sake of for a far away distance we are taking it as infinity. So we can say that the potential difference between any 2 points VB minus VA, it is the work done divided by in moving the charge in between that points divided by the test charge value Q0. Now here, as VB is equal to VA on an equipotential surface, as the 2 points are at the same potential, VB is equal to VA, and this VB minus VA, this is 0. So because of that, WAB, the work done in moving the charge from in between those 2 points, that will also be Q0 into 0, which is equal to 0. This is the reason why no work is done in moving a charge on an equipotential surface. That is the first property. Then the second property, or just another property, which is the electric field vector is normal or perpendicular to the equipotential surface. So this is the reason why I had drawn the electric field vector normal to the equipotential surface. This is just a 2-dimensional representation, but actually it is normal, perpendicular, top. So why is this? So we have already discussed, as in the potential difference video, potential difference as line integration of an electrostatic field. Potential difference as line integration of electrostatic field. In that video we derived that the potential difference between any 2 points in an electrostatic field, it is the negative line integral between the electric field vector and the displacement vector in between those 2 points. This is the dot product, this is the dot product. Now we know that dot product between 2 vectors, it is expressed as A B cos theta. This, where this is a vector, the magnitude of A vector, B is the magnitude of B vector. Now here again, on the equipotential surface, VB and VA, it is the same. VB is equal to VA again, so this means it will be 0. So as this is 0, it means E dl cos theta is equal to 0. That implies cos theta is equal to 0. That implies theta is equal to cos inverse of 0, which is equal to 90 degree. That's why the electric field is normal or perpendicular to the equipotential surface. It means that the displacement vector and the electric field vector, the angle between them is 90 degree, and dl here means the displacement and electric field vector, it is at 90 degree, means that the electric field vector is perpendicular to the surface, to the equipotential surface. Only then the displacement vector and the electric field vector, they can be at right angles or 90 degree with respect to each other. So this is the this property, electric field is normal or perpendicular to the equipotential surface. Then we have this property called as the equipotential surface. They give us the information about the strength of the electric field. Okay, it gives us information about the strength of the electric field. Now again, we know that the potential difference between 2 points, okay, it is given as the negative line integral of the electrostatic field, this previously which we just discussed. So we can say that dV by dl, this is the electric field vector, okay, the electric field, this minus dV by dl, minus dV by dl is this electric field. So here we can say that here the change in potential dV and the displacement, okay, dl, they play an important role in determining the strength of the electric field. So suppose there are equipotential surfaces. Let me do it in a separate, okay, let us say we have equipotential surfaces like this. This is equipotential surface 1, and then we have another equipotential surface, let's say we call it 2. Equipotential surface 1 has potential V1 and equipotential surface 2 has potential V2. Okay, so all the points on equipotential surface 2, they have potential V2, and all the points on potential surface 1, they have potential V1. So the difference between all these points, between surfaces 2 and 1, it will always be fixed, that is dV is equal to V2 minus V1. Here V2 is at a higher potential than V1, that's why I am saying V2 and V1. So for a constant dV, here as dV is constant, for a constant dV, since electric field is minus dV by dl, if this dV is kept fixed, if this is kept fixed, then electric field is inversely proportional to the displacement or the spacing gap between these two equipotential surfaces, this gap in between equipotential surfaces. So the smaller the gap between these two equipotential surfaces, okay, the smaller the gap, the higher the electric field strength. Okay, you understand? Since equipotential surfaces are at a fixed potential value, so dV will always be fixed. The difference between the points, potential points, will always be fixed. So when it is that, electric field is inversely related to the displacement or the gap between the equipotential surfaces. So the more the number of equipotential surfaces in between 2 points, then the gap will be as small as possible. dl will decrease, and as dl will decrease, the gap will decrease, electric field strength will be more. So the more the crowded, the more the number of equipotential surfaces, the stronger the electric field. You get the point? Okay, more number of equipotential surfaces means, let's say we have one surface like this, then immediately below that we have another surface, then immediately below that we have another surface like this. This is one situation, and in another situation we have like this. So here the gap is more, okay, it means dl is more. Here the gap is less, okay, the gap between equipotential surfaces is less. All of these equipotential surfaces will be at different potential values, okay. Let's say we call it VA, VB, VC, all of them are at different potential values. So it means the gap, the potential value between V1 and V2 will be fixed always. The potential value between 2 and 3 will be fixed. In all these cases, the potential value between A and B is fixed in between these two, and also in between DVBC, potential value between B and C will be fixed. But what is not fixed? The gap between equipotential surfaces. So where the gap is more, electric field strength is less, and where the gap is less, in that case the electric field strength is more. So here in this case the electric field strength is more, here in this case the electric field strength is less. Okay, this is how electric field is related to the number of equipotential surfaces in between 2 points. Okay, so this is the equipotential surface. It gives us information about the strength of electric field. Then so here we have another important property which says that two equipotential surfaces can never intersect. Okay, so let us try to understand this. See, let us say we have an equipotential surface here. Okay, this is one equipotential surface, let's call it, let's say VA, and we have another equipotential surface like this. VA is different from VB. Okay, let's say VA is greater than VB. This arrangement of equipotential surface is possible. Okay, it is possible. All the points on the surface A, they are at the same potential VA. All the points on surface B, they are at the same potential VB. Now let us say we have a situation where we have two equipotential surfaces intersecting each other. It means, let's say, surface X and Y having potential Vx and Vy. Okay, Vy. Now let us say they intersect at this whole region. So it means in this region the potential is both Vx and Vy. How can that be possible, that two different potential exist at the same time? It is not possible. Vx is different from Vy. How can Vx and Vy be equal at the same point? It is not possible. So it is because of this reason two equipotential surfaces can never intersect, because all the points on them are at the same potential, and if No, they intersect. It means at the intersection point we would have two values of electric potential existing at the same time at the same point, at that point, and that is not possible. Okay, so because of this, two equipotential surfaces can never intersect. Okay, so here we have discussed about equipotential surfaces and all the basic concepts related to it, the properties and related things.